Okay, in this video, we're going to talk about the I2C bus. The I2C bus is a synchronous serial data bus used for communicating between onboard ICs, usually between a microcontroller and some kind of peripheral. This is a serial bus. There is the document on serial communications should be read ahead of time so you can get an overview on serial communication protocols and especially bit synchronization and why we have these different protocols and what is the difference between them. So that would be good reading before this video. The I2C bus is originally developed by Philips, which is now NXP, and they developed it many years ago. It was originally known as the IIC bus, or the Inter-Integrated Circuit bus. So inter-integrated circuit describes a communication system that communicates between integrated circuits. And so it has the characteristic of being very inexpensive and fairly fast. Okay, the Kinetis K65 data is in chapter 58 of the reference manual. And this is the first time we've encountered this in the course, but there are some terms, namely the master-slave terms that's used for a type of medium access control protocol, along with all the pin names, especially in SPI. The description of what I'm doing in this class is in this deprecated communication terms. I'm replacing those terms with more appropriate technical terms. So you may see in the data sheet one term used, and in my notes a different term used. Okay, so let's kind of give an overview right now of the I2C bus. Like I said, it's a synchronous serial system, and it's synchronized with a separate clock signal. So that means we're going to have a data signal and a clock signal. So it's a synchronous serial system with a separate clock. It's used for either point-to-point communications, which means from one device to another. So let's look at that. We could have, say, an MCU. And that can be communicating to some other IC. Okay? And so point-to-point would mean that these two signal lines, the serial clock and the serial data, are just tied directly from the MCU to the IC. Now, the clock, if the MCU is the controller, and this is the peripheral, this is normally the case. Sorry about the squeezed in words there. If this is the controller and this is the peripheral, the clock is generated by the controller and the data is bidirectional, right? So the controller can request to write something to the IC, or it can request to read from the IC. All right, so that's point to point. But this system can also be used as a bus, which means we could have multiple peripherals. So another IC peripheral. And you can see these are all connected to the same lines. And we could even have another microcontroller. Okay, And all of these are connected to the SCL. Signal is all connected to the SCL pins of all these devices, and the SDA is connected to all the SDA pins on the devices. So this is a bus system because we have multiple devices on this same two lines. Well, I purposely showed a microcontroller here and two microcontrollers, a microcontroller here and a microcontroller here, because this system allows for a multi-controller system where this microcontroller can be a controller and this microcontroller would then be a peripheral, or it can at different times switch to this microcontroller being the controller and this microcontroller being the peripheral. And that's called a multi-controller system. So we can move the controller from one device to another. Now typically these ICs are always peripherals, okay? And yeah, let's talk about these ICs. These ICs are typically temperature sensors. The ones on the K65 board is an accelerometer. We'd have pressure sensors, all different kinds of sensing devices that can communicate back to the microcontroller over this bus. And what that allows for, and this is becoming very popular, it allows for a system like this to be designed without having to do any analog electronics between a sensor and the microcontroller going to an A to D converter, okay? Because we can have analog electronics in the IC, which then sends the data, there's A to D in there, and it sends the data digitally over this bus. So that's becoming very popular. Now, because we have the potential for multiple controllers, then this clock line also has to have the capability of being bidirectional, right? So this clock line sometimes may be coming from this controller, it may be sometimes coming from this controller down here, right? So that means that all of these outputs must be open drain. So they're all open drain outputs, and we need pull-up resistors on both signals. All right. So we need these pull-up resistors. Now, the typical value of these resistors is 1 k ohm. The value on the K65 board is a 4.7 k ohm. Usually anywhere between 1 and 10 k is going to work. What you have to watch out for is the larger this resistor is, the slower the rise time is going to be. And so your peripheral device, one of these peripheral devices, may have very specific rise time requirements. And so if you get too big, if you put a 10K here, the rise time of the signal may be too slow for one of the ICs. On the flip side, if we go to 1K on here, then it's going to be nice and fast, but the trade-off there is power consumption. So the smaller this pull-up resistor, the more power consumption, the bigger the less power consumption, but slower, okay? All right, so so that's the system. You can see we can go point to point, we can go to a bus system. Now, the way that this controller determines which peripheral we're communicating with is through the protocol of the data sent over the data line. So basically what happens, and as we'll see next, is the controller will send the address of the peripheral over the data line first. That tells, say it's the address of this peripheral, that tells this peripheral that the controller wants to communicate with it. These peripherals see, well, that's not our address, so they ignore the communication. And so that's how it's the controller selects which peripheral to talk to. Different than the SPI bus where we have a electrical chip select line going to each peripheral, and we select the peripheral by choosing the chip select. Okay, so let's take a look at the standard I2C read and write sequence, the timing. So here we have the clock line and the data line, and this is a general I2C read and write sequence. So this works for pretty much any peripheral, okay? At least I haven't found a peripheral that this doesn't work on. This is part of the I2C standard. All right, so now the peripheral may have more on top of this, as we'll see with the accelerometer, but this is the basic I2C. So here are the steps, 5 steps to read or write to a peripheral device. The first step is that the controller generates this start signal. And the start signal just, you can see that on both the clock and the data line, the line starts out high, right? Because these are open drain devices. They're not communicating, so the pull-up resistor pulls the line high, and that's the idle. That's an idle line because it's just sitting there high. All right, so the first step is that the controller generates a start signal which pulls the line low. So all of those devices on the bus see the line going low. And they go, watch out, controller wants something. And then the controller sends a 7-bit address plus a read-write-not bit and 9 clock cycles on the clock line, okay? So this is the address. And so the controller sends out a 7-bit address, okay, AD1 through AD7, while sending out these clock pulses. And these clock pulses are used by the peripheral to shift this data into its input, right? So we have a 7-bit address which addresses the peripheral and a read-write-not bit. And so if this is a 1, then the controller is telling the peripheral that it wants to read data. And if it's a 0, the controller's telling the peripheral that it wants to write data, okay? Then on the 9th clock cycle here, you see this is 8 clock cycles. So then on the 9th clock cycle, the peripheral pulls the data line low. All right, and that's an acknowledge bit. That's telling the peripheral, hey, I got your message. I see that you want to talk to me. So I'm acknowledging that by pulling this line low. If this line doesn't go low, there is an error flag in the I2C registers, status registers, to indicate that the peripheral didn't hear you. Maybe the peripheral's not working, whatever, but the peripheral didn't acknowledge the response of this address. And you can see this is after the address, so this acknowledge bit comes from the specific peripheral that we just addressed. Okay, so then we can have the clock is held low for however long. This could be low or high, so in other words, this acknowledge bit can go high. It has to wait for a while. It has to wait 1 bit time. And then it can go high or it can stay low. It doesn't matter. And then the controller sends 9 more clock signals, while if it is a write, the controller sends this 8-bit data with the 9 clock cycles. The 9th clock bit, there's no acknowledge bit in that case. Okay, we're sending data from the controller to the peripheral. That's a write. If this was a 1, then we're reading data. So this data is not coming from the controller, it's coming from the peripheral. But the controller is the one generating the clock cycles. So the controller generates these clock cycles, and that clocks the peripheral data out of the peripheral to the controller. And then in this case, at this point, there's no acknowledge bit, so the line stays high. And then the controller sends a stop signal. And that says, okay, we're done with this communicating sequence, and the line goes idle. Both lines go idle. All right, so that's the general sequence for a read or a write. So let's look at some of the code we need to generate this. First, the initialization. It's pretty straightforward. First step, of course, is turning on the module clocks. So we're looking at I2CVideo module. I mean, you can tell that I2C is an important communication device, since the K65 has 4 of them. So that tells you something. And if you have 4 separate I2C buses and each one could have multiple peripherals, that could be a lot of peripherals. So anyway, we're turning on I2C0, and the data and the clock lines are on port E bits 19 and 18. So we also have to turn on the clock for port E. All right, then we set up the port E control register for pin 19. We set the multiplexer to 4. That connects the I2C out that pin instead of, say, the general purpose port E port bit. And then we also set it to be an open drain. This is open drain enable. We set that to be 1. Okay. And the same with pin 18, we want to make that multiplex 4 and an open drain output. Now, you might say, okay, we had those pull-up resistors on the 2 pins, and this is an open drain. Can't we just use an internal pull-up resistor for that port, right? In the port control, we can turn on a pull-up resistor if we wanted to. Well, it's important to note that that pull-up resistor, the internal pull-up resistor, only works for inputs. It does not work for outputs. And these pins, like the clock pin of the controller, is always going to be an output. So we can't use internal pull-ups. Okay, so we set up those port bits. And then we set up the clock. I'm writing a 2C, so that sets up the clock to 104 kilohertz. The standard for I2C is 100 kilohertz or 400 kilohertz. And so 104 is the closest we can get with our 60 megahertz bus cycle. But that's fine because this is a synchronous system, so we have the clock signal clocking in the bits anyway. So 104 is fine. Then we enable the I2C module, and that's setting this bit to 1 in the control run register. So it's fairly simple to initialize the I2C. All right, so let's look at an I2C write. Okay, I brought the timing diagram along with us so we can see how this works. This is just writing 1 byte out the I2C bus. All right, so the argument is it says D out for data out, but that data out could also be the address, right? And so the way this works is that we just write this data that was passed to this function. We write that data to the data register of the I2C0, and that generates the 9 clock cycles and puts the data onto the bus. So the first write, this data might be the address of the peripheral, right? The first time we do an I2C write, this data is actually the address and the read write not bit that's going out to the peripherals. All right, so that we do that, and then we wait. We have to wait for the transmission to be complete because, you know, we write this data to the data register. It automatically sends this clock out and shifts this data out. But, you know, this data is at 104 kilohertz. So that takes, you know, in MCU time, that's quite a while. So you don't want to do other things while this is still shifting out. So this is waiting for it to finish shifting out. So it does block a little, and you have to be aware that this write is going to block a little, and then it clears the flag when it's done. Okay, so fairly simple write. And so if we wanted to write to a peripheral, we would do an I2C write with the address. Then we would do an I2C write with the data that we wanted to send. And then, well, we would send a start first, a write, and then a stop. Okay, so this sequence would take 2 of these writes. All right. A read, a little more complex. We have to change the direction of the data register here. Okay, so a read, the parameters are, we don't pass anything to it, and the value coming from the peripheral ends up as the return value. So we have a little local variable for that return value. Okay, the first thing we have to do is change the controller to receive mode. So we're actually kind of changing the data direction there. And then we're saying that there is no acknowledge in this case, because it's always going to be the last of the 2 bytes that we send out. So there's no acknowledge in this case. Okay, then we send a dummy read. So what that means is that we read, since we're in the receive mode, when we read the data register, it sends out clock cycles, sends out 9 clock cycles. And so those 9 clock cycles, we're not outputting anything because we just turned the transmit mask off, so we're in receive mode. But when we read this data register, it sends out these clock cycles, which then clocks the data from the peripheral into our controller. So here's, we're waiting for that data to be shifted in. Then we clear the flag, and then we do a stop. It's the stop here. Okay, and then we know the data register is going to contain the data that we receive from the peripheral. So then this time it's not a dummy read, right? We ignored this data in, but we receive this data in and we return the value. So if we wanted to do this, this process here for a read, then we would do the I2C write to write the address here. And then we would do the I2C read to read the data from the peripheral, right? And that would also include the stop. Okay. All right, so real quick here, here's the basic I2C stop and start. It's fairly simple. We have to wait for, to do a stop, we want to wait for any transfers that might be going on to complete. So we're watching this transfer complete flag. That's a little different than the that other IIC flag. This actually means that last bit was finished going out the pin. So we have to wait for that, and then we basically make it a stop bit, and we make it not transmit anymore, so it goes into receive mode. Okay, and the start bit, we have to wait for an idle bus, right? So there's a busy mask or a busy flag in the status register, and so we wait for the idle bus, and then we turn it into transmit because we're going to start transmitting data, and we set the start mask bit. Okay, all right, so that's all there is to the basic I2C. In the next video, we'll look at a specific peripheral. We'll look at using I2C to communicate to the accelerometer on the board. but in that code, we'll be using these basic I2C functions as a building block to communicating to the peripheral.